aromatic reactions. If I was to follow the book's order, then we would actually end up discussing things like spectroscopy that have nothing to do with the aromatic compounds necessarily. Okay? All right, so this next chapter, 24, is the one we're going to be on now. This will be the last chapter before the exam. Once we cover this, you'll have that review assignment, right? Did everybody see the review assignment? Nope, that's good because it isn't posted. Okay, that's actually going to be posted sometime today, probably. I've started working on it, so thank God you can't see it because otherwise somebody would try to complete it. Would have only had some of the questions. So the aromatic substitution, this is going to be the first part of the aromatic substitution. We won't probably be able to get to the second part. We just don't have time. Okay? So you'll forever not have all of the aromatic substitution reactions you could possibly have. I know. It's sad, and your lives will never be complete without it. All right. So this is going to be the substitutions on benzene and some useful accompanying reactions that would go along with that. So here's the benzene ring right here, right? And we had already discussed this portion right here where a lot of the reactions that we would normally be able to do with a double bond, we just can't do with benzene, can we? Why is that?
It's the resonance.
Yeah, the resonance, right? If we have to put this normal carbocation we make here on this, we would break our aromaticity, right? Our resonance structure. And so we end up with no reactions for things like HCl, Cl2, and most of these reactions. Now there is ways you can approach this benzene ring to get around that limitation and start doing very similar reactions, okay? So the electrophilic addition reactions that permanently disrupt benzene's aromaticity, these are going to be heavily disfavored because you would have to overcome a activation energy that would involve breaking that benzene ring's aromaticity, right? Which boosts that way up and makes this incredibly slow and incredibly energy inefficient. The lack of reactivity is going to be attributed again to stability that's exhibited by the benzene aromatic pi system. This is true, though, for all aromatics that are actually aromatic, not anti-aromatic, right? Yeah. So in all of these cases, you have to break that aromaticity, and that makes that very unfavored, right? Or disfavored. So right here, we can actually see an aromatic substitution. This aromatic substitution actually functions and works. We actually get a yield from this. And so we take here benzene. Notice we're expressing that hydrogen, and so this hydrogen has something to do with it, doesn't it? And we're going to react this benzene ring and replace that hydrogen, in this case, with that chlorine. Okay. You'll note that this has some pretty interesting reaction conditions, doesn't it? See that iron chloride? You don't see that very often, do you? We have a metal with a salt. Yeah. So it requires its own sort of set of conditions. So with the iron metal or iron chloride, it's going to be added to the reaction mixture. The benzene does react with Cl2, but we don't break and add across one of the double bonds. Instead, we end up substituting that hydrogen on the ring. Okay? Notice that right there is not part of the aromaticity, is it? And so we begin with aromaticity, we end with aromaticity, don't we? And that avoids that issue. So again, we'll get a substitution. We preserve the aromaticity. That's very, very important. Now, the general mechanism for these electrophilic aromatic substitutions is going to be this mechanism here. Now, this is that general mechanism that you really just have to substitute whatever you're actually using in for this E, right? And it could be a whole variety of compounds. So it's like me giving you a whole set of tools, right? Like you'd get one of those kits of ratchet wrenches, right? And you can swap whatever head you want. Okay, now when we're doing this, notice that again, our mechanism has a very straightforward naming, doesn't it? So we have electrophilic. Electrophilic means it is something that wants electrons, right? Okay. And so it loves electrons. It's usually something positive, but it doesn't necessarily have to be. Just, it's something that's going to pull electron density, right? And then it's going to be an aromatic substitution. So it's going to work on aromatic rings. It's going to cause a substitution onto the ring. It'll keep the aromaticity. Okay? That's the important key notes that you want to see whenever you see that reaction name. All right? So then we're going to go ahead and do this mechanism. Notice that this right here is where this begins. We're then going to end up with a resonance structure. Anytime you do anything to an aromatic ring that's going to cause any charges on it, you're going to end up with this sort of resonance structure, okay? And that's because what makes aromatic rings so stable? Resonance, right? Yeah. So anytime you do something to them, you end up with usually 3 resonance structures, but sometimes a few more. This right here, again, is going to be the electrophile right there. It's going to be positively charged. You're going to pull electrons from one of the double bonds. This will temporarily disrupt the aromaticity. Okay? And so we'll disrupt the aromaticity. This will give us this resonance structure that does help to minimize the energy of this intermediate here. This is called the rhenium ion intermediate. So it's a resonance stabilized carbocation, isn't it? Okay. Can everybody see it okay? Okay. What does this mean about this structure, by the way? Where are positive charges located? So are these 3 different structures? No. Resonance structures are actually the same structure, right? We just need 3 different versions to fully accommodate it, fully understand it. So our positive charges end up here, here, and here. See that? Okay. So did we necessarily have to do this mechanism right here? Is that the only place we could have done that? No, we could have done it up here, right? Yeah, you could have done that same mechanism either place. This just happened to be on the bottom. So there you go. So we're going to then take a base. This is going to remove that hydrogen. And this is going to let the hydrogen's electrons go into the bond here to reestablish our aromaticity. Okay. And so that will then be the electrophile elimination step. And this will reestablish our aromaticity and give us our substitution overall. Okay. You'll notice that this is again an addition, elimination, substitution. We've done that a few times now, especially on things like double bonds, right? And so this is actually the same sort of thing we'd seen before. It's just an aromatic system now. Okay? Yeah, we don't really have a lot of completely new stuff in this course. The spectroscopy will be the completely new stuff, I guess. Okay. Does anybody have any questions? Nope. So old hat, the only addition being doing it to an aromatic system, right? Okay. Addition, elimination gives you an overall substitution. Okay, so let's go ahead and look at the energy states. This right here is going to be that elimination. It's going to be a quite high energy transition state. Now this more stabilized intermediate than it would normally be does help it out because it has the 3 resonance structures. And so that did lower it a little bit, but it is still pretty dang high energy, isn't it? Okay. And then what we're going to get is the rhenium ion is going to have the intermediate here. It's going to lose the H plus to a base, and that's going to go to product, which is energetically favorable, right? Okay, so if we look at the kinetics of this reaction, we would have the rate equals K, which is the rate constant. And then we would have our substrates right here, won't we? Okay. Why doesn't this have like the base in it or any of that stuff?
Takes away the hydrogen.
Yeah, so our slow step is, was that what you're going? Okay. Our slow step is this step right here, right? Yeah. And so whenever you do a rate law, it's always for the slow step, right? This one right here is very high energy. And so this is going to go real fast because we only have to jump up a very small amount, right? Okay. Okay. And so our rate law is always defined by the reactants or substrates for our slow step. Okay. And that's these right here. Can anybody tell me if that's first order or second order overall? Overall, it's second order. Individually, for these two reactants, it's first order. Yeah. To the power of 1, right? Okay. So it's for benzene, it's first order. For the electrophile, it's first order. Overall, second order, because it requires two things to come together. That's molecularity of bimolecular, right? Okay. Yeah, I'm doing a little review there. Okay, so these reactions are generally considered irreversible. They take place under kinetic control. Remember that irreversible reactions, you won't be able to go back and forth. And so they're always going to be whatever goes fastest is the one you're going to get. Okay, so again, this is the halogenation. If we try to halogenate this with a typical addition reaction, we get no reaction for an aromatic ring. If we take this and undergo the electrophilic substitution, we can go ahead and get a substitution right here, and we'll get a yield of about 97% under these conditions, which is quite good, isn't it? Yeah. Notice that these are not actually that drastic conditions, are they? No, that's actually pretty nice. All right, so this right here is actually the bromination mechanism. This is the one with the Lewis acid catalyst. And so right here we see the iron bromine. The first thing we're going to see here is a coordination reaction with the Br2 to make that the reactive species, i.e. we're generating our nucleophile, aren't we? Okay. Bromine is not exactly the easiest thing to make a nucleophile. And so we can't like go to the store and bam, there we got it. Okay, we have to make it in solution, don't we? And so we'll take the FeBr3 coordination reaction with Br2. This is going to give us this right here, which is going to be our reactive intermediate here, generated in solution. And notice that we have put a positive charge on this Br because these other Brs are pulling electron density from this, aren't they? Everybody see it okay? Okay. Then what's going to happen is this is then going to be your electrophile. That's very strongly electrophilic. This is going to take the electrons from one of the double bonds. Is there something special about this position right here? No, that's every carbon in the ring, right? Every carbon in the ring had one hydrogen. Okay? I'm just making sure nobody gets a weird idea. All right. So we're going to go ahead and attack, pull electrons from the double bond. Those are then going to allow you to pull the electrons from the Br-Br bond onto this Br, which will remove its positive charge. Okay. And so we then end up with the addition right here. Note that that would have those resonance structures that we had shown before. I just don't have room for them here, right? Okay. And so the next step here is this now is a pretty decent base. And so this hydrogen right here is going to be lost. This is going to be the electrophile elimination. And this is going to use the electrons in this Fe-Br bond, where the Fe is negative. It's going to take the electrons into a bond now, coordination bond, with that hydrogen. That's a normal acid-base reaction, or proton transfer. And this is going to leave those electrons behind, which will flow over to the carbocation and make a double bond. Okay, notice that in the end of this, we have restored aromaticity. Yay. We have regenerated our Lewis acid catalyst. Yay. So our catalyst is still there. And we have made HBr out of Br2, right? Okay. Okay. Did I lose anybody? No? Fantastic. All right, well, let's see if you got it. So everybody go ahead and get started on this problem. Try to make some real progress and see if you understood this and you can do this. So remember, I've given you a new tool to use so that you can now use that tool and build me something interesting. Don't forget your old toolkit. We are building, building, building up. Eventually, I expect you all to be Da Vinci. Except less kooky flying machines don't work. My goodness, my poor students are like undergoing a plague or something. It's been pretty wild. I've had so many sick notes over the last week.
Flu's killing.
Flu, mono. Keeps up this way, I'm not going to have any students left in like a week. And the whole city will be down in like 3 weeks. Okay, folks. So I'm going to go ahead and start getting started. Hopefully you made some decent progress here, or at least you revealed where you're getting stuck. Okay, so we're going to do this in a retrosynthetic pathway, right? Because we know the final product we want, and it's usually easier to work from the final product if you know it, right? And so the easy way to deal with this is, well, we want right here a ketone, right? A carbonyl. Usually the easy way to deal with it is to undo an oxidation, which would be to get the OH. You would do an oxidation if you're going in the forward direction to get the ketone, right? So, undo an oxidation. The next step here would be that we would need to undergo a Grignard reaction. Note that that typically works best by taking an aldehyde, and you would attack, forming a new bond right here, which would give you the alcohol, right? Okay. And so this right here would be your Grignard reagent right there. We will have to undo a Grignard reagent. Notice the BR here? Yeah. So we got back to something that we just talked about, didn't we? Okay. So the first step was undo oxidation from this to this. And then we take the alcohol, we undo a Grignard reagent reaction. This right here is the Grignard reagent. This is the thing we reacted to get this group on. Yeah. This is a chemical we would have to purchase or synthesize in a separate synthesis. You can purchase this, by the way. It's cheap. Okay. And so this right here, this is how you do a Grignard reagent, is you actually would take a Br, something with a bromide or chloride, and you'd put some magnesium metal with it, right? And this right here would be undo Grignard formation. The next step is going to be the one that we had just been talking about, right? And that would be undoing a bromination. And that would be this reaction right here. Okay. Did I lose everybody? No? Okay. Yeah. Keep in mind, whenever you're doing these, it's easier to work in retrosynthesis. Mm-hmm.
So I'm good after the bromination, but then how do we know to add the magnesium?
So there's actually a few ways you could go about this, but in my opinion, the easiest one would be the Grignard reagent. And we know that because right here, so as long as you get to here, you would recognize that you need some way to add on to here, right? There's a few ways you could do it. There's a few different substitution mechanisms. You could do lithium, copper, Grignard. Those would be the easiest ones. You could try to do something like an SN1, SN2, something like that. But a lot of the SN1, SN2s would be very difficult to do in this case and get an alcohol near it where you're reacting, right? And so in this case, I did Grignard, but you could have done lithium or cupric, organocopper. In this case, because we have the bromine, the Grignard's really easy here because we've already set it up with a Grignard, a fluoride Grignard. The Grignard reagent is the one where you swap in the metal ion, and it makes this an extremely good leaving group instead of just an okay leaving group. Yeah. It's not making sense?
Yeah, so then for it to leave, the electrons would go back into the benzene?
Yeah, so what you're going to see here is then this is going to attack this position right here. Okay. This is going to come up. We'll end up protonating that. And then we'll be left with the alcohol. Yeah. And now we have an oxygen attached to that location we wanted. Yeah. And so then we just have to do an oxidation to get the oxygen to be the carbonyl we want. Yeah. The reverse, so we want this to be our nucleophile that attacks that position. Getting this to be like an electrophile that attacks that position is going to be very difficult. Like this is going to be the more positively charged thing. And so we really want to work towards attacking that positive position. The presence of the oxygen just kind of eliminates a lot of the reactions we could have done the other ways. Because the oxygen is going to pull electron density, right? Did that make sense?
Yeah.
Okay. Okay. Did that answer the question? Okay. All right. So this is the iodination. You'll notice it's a pretty similar reaction, but again, bromine and iodine have slightly different reactivities, right? So you can't necessarily depend on bromine and chlorine doing the bromine and iodide, doing the exact same thing. So the iodination, this is slow. It can be carried out in the presence of oxidizing agents like copper 2+ or hydrogen peroxide. The oxidation of I2 is actually going to generate I+. This can then enter into the electrophilic aromatic substitution mechanism because that's a pretty good electrophile, right? By the way, has anybody ever seen a similar reaction with copper and iodine? Okay, this is oftentimes used as what's called like the clock reaction because it's actually very dependable time amounts and it generates like a nice purple color and you can put starch in it to generate that color. Yeah. And so what you do is you take copper in a salt and it actually ends up reducing from copper 2+ to copper 1+, and you get I3- in solution. Okay, kind of an interesting thing. Anyways, so this right here is going to be the Friedel-Crafts alkylations. And so you'll notice we are using a very, very similar mechanism to what we had just talked about in terms of the bromination. And so here we have a compound that's a chloride that's attached to some alkyl group. Okay, in this case right here we have a nice butyl group, right? Nice terp butyl. Okay, can everybody see those? Okay, and the commonality between them. Fantastic. Okay, so what we're going to put is aluminum chloride in there. We're going to heat it for well, usually you keep it at a fairly low temperature, but it'll take some time, okay? 2-3 hours usually. And you'll get the alkylation at this spot. Okay, let's go to the mechanism. So the first step of this, notice these are very, very analogous to the previous mechanism we looked at. The first step of this is going to be the aluminum chloride here is going to have undergo coordination with the chloride on your alkyl chloride. Need my water. All right, and this is going to then form that same negative charge in the metal that's being stabilized by these 3 halogens, pulling electron density away. and positive charge on that chloride. So notice that chloride right there does not like having a positive charge on it, right? If we look at periodic table, it's one of the more electronegative atoms on the periodic table, right? It's about the same electronegativity as oxygen, isn't it? Okay. And so what's going to happen is it's actually going to pull the electron density from the carbon here. So it's going to pull that bond's electrons away. That's going to give you, in this case, a trigonal planar carbocation. Everybody see that okay? Now notice that one of the things that is important about these reactions is this has substituents that are going to stabilize that carbocation that will help this carbocation stick around and act as an intermediate, right? So this right here is a very, very powerful electrophile, isn't it? And to do these reactions where we temporarily break the aromaticity, we need powerful electrophiles. So this electrophile is going to break the aromaticity. It's going to pull the electrons that are in that double bond. That's the electrophilic addition step. That's then going to give us the carbocation on the aromatic ring. Once we form that, this H here is going to be very acidic, and so it is going to have its electrons pulled over to the carbocation, be very acidic, and it will pull the electrons from this chloride aluminum bond here, which has a negative charge. That will then act as the base, right? Okay. And that's the electrophile elimination. And again, we end up with very similar products here. So we end up with HCl, aluminum chloride, and we have our substituent. Did I lose anybody there? Okay. Okay, so again, we're actually just generating a carbocation in situ, which is a very powerful electrophile, right? And then the electrophile is being used in the electrophilic addition, and then we get the elimination to finish off the substitution. Okay. Can everybody see how analogous that is to the bromine? Note that these metal ions, it actually is important what these metal ions are. Okay. These are Lewis acid base reactions, by the way. Anybody recognize Lewis acid and base reactions from Gen Chem? I know, right? You can actually do about 70% of organic chemistry just from understanding Gen Chem 1 really, really well. Because almost everything is Lewis acid-based reactions, orbitals, and Bronsted-Lowry acid bases, right? Okay, so these are some of the other alkylations that you can undergo, and they're all fairly analogous reactions in these cases, okay? Essentially what we end up doing is we form some sort of carbocation in these cases, right? Once we have a carbocation, that's a powerful electrophile, right? And we undergo the exact same reaction. Is that making sense? So notice, I'm not teaching you 5 reactions, am I? I'm teaching you 5 starts to the same reaction. Okay? Generate my powerful electrophile, attack with my powerful electrophile, breaking the aromaticity, and then regenerate the aromaticity by losing a hydrogen, right? That's the reaction for all these, isn't it? Okay? Only difference is how do I generate that powerful electrophile, right? And those were all things that we've actually learned in previous chapters and done, like this reaction here, I think you've done something above 60 times. You know this is the H plus goes on to the OH generating H2O plus, right? Which is a really good leaving group. Which hopefully at this point you're like, oh God, Dr. Clausen, stop beating that horse. It's over. It's over. It's done. We've seen it. Okay. Okay. Does anybody have any questions about these? Mm-hmm.
How does the bottom one reach out initially?
H plus goes on to the double bond, generating carbocation. And then carbocation does the electrophilic.
Okay.
That making sense? Yeah, it's the same start for all the acid catalyzed additions. that we had done. And this is in fact acid catalyzed addition elimination. Yep. Acid catalyzed again up here. Okay, so let's go ahead and test it. Show how to synthesize the following compound in a single reaction using benzene as one reagent, and these other options, alkyl halide, an alkene, or an alcohol, as the other reagent. Okay. Now, if you ever had to draw this out, there's a smart way, and then there's a long way. I just had mentioned that all of these reactions end up getting to the same endpoints, right? So like 2/3 of the reaction that you'd have to draw, you could just draw it once, couldn't you? Yeah. And then all you gotta do is just set up the first part for each of them. So what do you think? This fit well with the previous chapter? It kind of does, doesn't it? Okay, folks. Anybody still making real good progress and still exploring your limitations and where you're getting stopped and stuck? Okay, I'm going to go ahead and start going. And so what we're going to do here is essentially we're just going to have to do this where we generate the electrophile to do the substitution, right? Okay, so all the rest of them are the exact same mechanism after we generate electrophile, aren't they? We could just put E plus, and that's that mechanism for that part. That's it. So they're all going to end up being.
So is that? Oh, yes, electrophilic aromatic substitution. Okay.
Yep, you got. Yep, yeah. Undo the electrophilic aromatic substitution, exactly. And this right here is your electrophile right there. This right here is the benzene ring, right? Does it matter which side we do this? No, it's symmetric, right? So, doesn't matter. Okay, so the next part is, this is where we actually have some sort of branching, right? And so what we're going to do here is for the chloride, we need, for the halogen, chloride is the one I've shown you, right? And so you're going to put the chloride. See, I've taken this part right here, and I've just added a chloride, right? And my group on each of the ones that I'd want to do. So we put the chloride here, and the conditions is aluminum chloride, right? That's the other reagent we need. Right here, we have a double bond, so that's the alkene one. And then we have to go ahead and put the H plus here, okay? Everybody okay with that being there? On the end there? Yeah. It kind of has to be, because if we tried to put it here, we couldn't do it. There's not enough positions, not enough bonding positions. But in this case, actually, the H plus will go with the more H's, right? The carbocation will go on the more substituted side. So it works out either way. This right here then is going to be that acid catalyzed alcohol again. And so we have the alcohol in this position. That would be that protonation of the alcohol to make that great leaving group H2O plus, right? Once that leaves, we have our carbocation. Those all generate our carbocation, which is going to be our electrophile. That's going to attack a benzene ring. And that's going to generate our final structure here. Everybody okay with that? And this is what I was hinting at. You can just go ahead and go into a single structure for all of them, because they all end up in the same place. They have to. Okay. Okay. All right, so let's talk about some of the limitations of our new tools. So the limitation of Friedel-Crafts alkylation. Now, honestly speaking, I don't find the naming of these reactions particularly useful or helpful. Is anybody super interested in becoming like a full-on organic chemist? I'm going to do synthetic synthesis lots and lots and lots. Yeah? No? I guess not. Okay, if you are interested in this, those people like memorize the named reactions. Okay? Because it's like a craftsman familiarizing themselves with their tools and making sure they know which pockets they're in, right? So they can come up real fast, easily to mind. Okay? So, what are some of the limitations? Now, if we are generating carbocations, what's an issue with carbocations? What happens when we generate a carbocation? Yeah, we get rearrangements, right? Carbocations are very high energy, and so they're going to have hydride shifts, methyl shifts. They're always going to go towards the position they're the most stable on, right? So let's say we try to do this reaction right here. We're not going to get the carbocation right there, are we? And so we can never get the substitution on this position, can we? Yeah. So this is never going to happen. It's a minor product, and you might get a little bit of it, but it's just not ever going to be the major product. You're going to have a lot of difficulty ever getting this structure out. What's going to happen is you're going to get a hydride shift, and your carbocation will be that position, won't it? Why is that position the more it's more stable? Benzene ring. Yeah, the benzene ring gives you resonance structures, doesn't it? Yeah, so this will be the major product right here. And again, that's that dang carbocation doing a rearrangement, isn't it? Right? And anytime you generate carbocations, that's always a concern, right? Because carbocations are very high energy. They tend to do lots of rearrangements. That's why we've, what have we done, like 30 problems with carbocation rearrangements in my various homework modules? Yeah, because carbocations are a very major part of organic chemistry. Lots of rearrangements happen, lots of problems, right? Okay, now this right here is the partial mechanism. So we would generate a carbocation and we get a hydride rearrangement. That would put the carbocation right here. This is then going to be the carbocation that's going to do the electrophilic addition. And then we'll get the elimination and our final product. Notice the blue position was where we started with it, carbocation. Okay. I didn't lose anybody up to now, right? Okay, fantastic. Okay, fantastic. Now, again, this is another example of another rearrangement. So here we had the chloride on the primary position, right? And so we generated our carbocation. Primary carbocations are not stable, are they? And so where would our carbocation actually move to? The secondary position, right next to it, right? Yeah. And so we start off, we generate our carbocation. We on the primary position right there. And it's going to immediately pull electrons from the hydrogen next to it and move to the secondary position, right? And then it's just that hydride shift again. Remember that hydride shifts are so fast that they can actually join with other reactions. So for example here, we're actually getting this step here where we generate the carbocation. As soon as we start pulling the electron density, the difference in stability is so great, you're going to have those hydrogen electrons start just moving over into the void. Okay? And so you may not ever even see any of this carbocation at all if you were to monitor this. Yeah. Hydride shifts are really fast, right? Okay, so this is the hybridization requirement. This is also going to be something we have to consider and deal with. So the sp2 hybridization of your carbon is going to increase the strength of that C-Cl bond. Remember we had talked about greater S character in previous works, and that increased the strength of those bonds? Yeah, same thing here, right? So instead of having one S out of every 4, we have one S out of every 3, right? Orbitals. So 33% S character. And so this is going to have increased the strength of the C-Cl bond, and it's going to decrease the stability of your carbocation that would then be produced. And so, for example, if we tried to pull that same stuff on this right here, which is your benzene ring, right? You're not going to be able to do that. Okay? It's going to be too high energy to generate that carbocation. And so, again, we can't do a Friedel-Crafts where it's directly on a benzene ring. This again is another example of this. This is just with the double bond next to it, right? So if you try to do a Friedel-Crafts and it has the double bond right next to that position, that's not going to work. Okay? Is there things we could do to try to sort of work our way around those, though? What if instead of next to the double bond, we did it one more position over? What would happen? Yeah, that position would be sp3 hybridized. We could do it, right? And in fact, the carbocation would then be stabilized by a resonance structure, wouldn't it? Pulling the double bond into a double bond there, leaving a positive charge there. Okay? And so we wouldn't be able to get our double bond right there, but we could play with it a little bit, right? We have some wiggle room. Okay? Okay. So these are things you have to keep in mind. These are limitations of your tools, right? Okay. All right, let's talk about polyalkylation. What do you think polyalkylation means? Yeah, many, right? Yeah, we just keep doing it. What is poly really used by chemists? I don't want to count. Right? It's really used by, it's happening sometimes, and I don't care how many. I don't have any ability to really count it. It's a poly. Okay? And so what we're going to get here is Friedel-Crafts alkylations. Oftentimes what's going to happen is you'd actually stabilize the carbocations even more. Okay? So those generated carbocations that you get on that mechanism right after the addition part, before the elimination part, those actually get stabilized even better by having these alkyl groups on it. And so you actually tend to get many alkylations, polyalkylation, where you add over and over and over. Okay? They actually add in very specific locations, though. And that's why you're actually seeing the single alkylation. You're then seeing, does anybody remember the language for this? Meta, ortho, para, right? Okay. Which one's meta? Next to it, yeah. And ortho would be? Para then would be? Opposite, yeah. Okay. So, meta, ortho, para. The other way is commonly mentioned. This would be one position, right? This would then be 1, 2, 1, 3. This one's 1, 4. Okay. The meta-ortho-para is used quite a bit as like an informal quick method of dealing with it. The other ones are used less often as quick methods because they require numbers. Yeah. All right. Anybody have any questions about that? Everybody understand polyalkylation happens because it's actually more stable to do it? Okay. Okay. All right, so let's talk about some of the Friedel-Crafts acylation. So if we have an acid chloride, oftentimes referred to as an acyl chloride, we can actually do this Friedel-Crafts, but we'll get an acylation. And so what's going to happen here is, again, we're going to generate that carbocation right there. We're then going to attack the ring here. And what we see is we actually get this where it bonds right there, and we get the double bond. Let's discuss how we actually have to go about this. So the first step is going to be the coordination, where we generate that positively charged chloride on there. This is then going to pull its electrons and give us the positively charged carbocation there. Now, once we've done that, this is going to involve heterolysis. Anybody remember what heterolysis is? Lysis meaning breaking, right? Hetero meaning unevenly. Okay? And so we break this bond here unevenly, leaving behind the electrons, right? Okay. And that gives us the positively charged carbon there. Now, notice that that is the acylium ion. It's a relatively high reactive electrophile. It does have a resonant structure there, though, which is kind of interesting. And so we have the positive charge on the carbon here, but it can also pull the electrons from that lone pair in the oxygen and form a triple bond, leaving a positive charge in the oxygen. This is an unfavorable structure, but it is part of the resonance structure for that. And so what's going to end up happening is we're going to pull the electrons from the double bond and the aromatic ring. This is then going to give us this structure here, and then we're going to do the loss of the proton to reestablish our aromaticity. Okay. Did I lose anybody in all that? Notice it's really just the same mechanism, except we generate a resonance structure here on our carbocation, right? Okay. Okay, that carbocation resonance structure here, this acylium ion, this is actually a pretty interesting, unique structure. And so this is the acylium ion. It's produced near Friedel-Crafts acylation. It's resonance stabilized again by a lone pair of electrons on your adjacent oxygen. Note that usually it's very difficult to generate a carbocation next to an oxygen because this is very, very high energy. The oxygen is pulling electron density, right? This is somewhat of a unique case because we have these extra lone pairs that can be donated and form resonance structures and help stabilize it a little extra. Okay. So note that because we have this structure, see that? Where we have that resonance structure. What would happen if we do any sort of hydride shifts or methyl shifts? We'd move that carbocation, wouldn't we? That would break this resonance structure, wouldn't it? And so if we use anything that generates an acylium ion, any Friedel-Crafts acylations, these are not going to be susceptible to most carbocation rearrangements, okay? Because we're stabilizing that carbocation in that location to a little extra degree, right? Okay. The Friedel-Crafts acylation as a means of formylation. Anybody know what formylation would be? Adding formal like formaldehyde. This is going to replace the H by a formal group. This is the formal group right here. And yes, that is having to do with formaldehyde. Notice formaldehyde has aldehyde in it, right? Formaldehyde was always an aldehyde. This requires in situ. Mm-hmm.
So, this Friedel-Crafts acylation thing,
Mm-hmm.
is that we technically, back when we did that Grignard reaction, undo Grignard reaction?
Yes, this would have been an option.
Okay.
Yeah. Yeah. Yeah, we just didn't do that because we hadn't introduced it yet. Yeah, but yeah, like I was mentioning, once you have the tools, there are many pathways. Yeah. Yeah, honestly, most of the reactions, if you guys go back through my notes, you'll see about half those reactions, probably more. You actually could have done other tools in the same chapter and gotten those. Yeah. So there was a whole variety of different tools you can use. And as we expand, you're going to start seeing that more and more. Yeah. Where you're like, why did we do it that way? Now, honestly, that Grignard one, though, was quite elegant. Because those are very high yield reactions and very easy to do. So it was not a bad choice. This also would have been a good choice, though. Okay, you'd have to test them for me. Run them both and find out. Okay. Now, this right here, because this only has the single carbon there, it's going to be less stable than the other ones. And this right here, which is the chloro one, that's that acyl chloride, that's going to be very, very unstable. Okay. And so this is something you'd actually have to take formaldehyde and some chloride source, and you'd have to generate in situ, in solution. You won't be able to buy this acyl chloride. Okay. Unlike the other carboxylic acid derivative chlorides, which you could buy. This right here is nitration. So we're going to take concentrated nitric acid. We actually have to keep it under fairly lowish temperatures. That's usually a problem for this because you can do this reaction over and over and get a bunch of nitro groups on it by accident. And so this would give you nitrobenzene, 83%. So what's going to happen in this reaction is you'll actually get the nitric acid reacting with itself. Okay? And keep in mind, this is a strong acid. And so the nitric acid is going to have a lone pair of electrons. It's going to aid in the prevention of your nitrogen atom from losing its octet. And we'll get a proton transfer between two of these nitric acid molecules. Okay? And this is going to give us this right here, which is a water leaving group here. That's a very, very good leaving group, right? Okay. And so this actually gives you the heterolysis then, which is the nitronium ion that generates. This is very unstable, very reactive. Okay, this isn't going to sit around in solution for long periods of time. Right? You can actually aid this reaction right here, generating nitronium ion, by putting in something that's a bit better of an acid, like sulfuric acid. Okay, and so then you can increase the amount of nitronium ion you generate, because you have more of the nitric acid already protonated. Yeah. Anyways, so the nitronium ion is going to be this very reactive electrophile. It's going to take that double bond electrons into a bond with the nitrogen here, leaving electrons up on this oxygen. That's the electrophilic addition. And then we're going to get the electrophilic elimination, which is going to be the loss of a proton to water, right? And then that right there is the nitration. That's the nitro group. Okay? And you'll notice it does have that charge separation there, which is kind of an interesting issue. I don't know if we'll be able to get super far into it, but these do actually cause some interesting consequences to this. For example, you have a positive charge next to that carbon there, right? So it actually, if you want to do more reactions, that's going to cause it to not want to have a positive charge here. Okay? So we're introducing lots of new tools, right? There's all sorts of fun chemistry you can do around rings. Good catch. Please. Good catch. Good catch, yeah. Yeah, I've been waiting. Yeah. Oh yeah. If you start going back in your notes on the reactions I've done before, in fact, you're gonna find places where my reaction I gave you guys was not a good option. Mm-hmm. 12:30. Uh-huh.
I have a question. So on Friday, I'm gonna be missing lab because I have a tennis tournament.
Oh my.
But I was wondering, we are supposed to leave at 11:30.
Mm-hmm.
But I was wondering if I could come at 8, from 8 to 11,
Yes.
and do the lab.
Yeah, you could join me. That's when I prep though.
Okay.
So it's not going to be super.
But 3 hours should be good enough to
Yeah.
finish the lab.
Yeah, you should be able to finish.
Okay.
Or at the very least get to the point where you can set it aside and finish it next week.
Perfect. Thank you so much.
No problem. Hey.
So my softball game got moved to Friday instead of Saturday because of rain.
Okay.
So I was wondering on Friday if I could come in early in
Sure.
the lab, like about 8 or something.
Sure.
You
Yeah.
can give me.
You'll join her.
Oh, okay.
Yeah.
Perfect.
I might have you guys like form a temporary partnership.
Okay. Perfect.
So.
Thank you.